Hello everyone, I am Sulekha Sharma and welcome to Sulekha Physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am coming with second part of chapter Wave Optics. In the previous class, we had discussed about wavefront, Huygen's theory, Huygen's construction, and today with using that Huygen's principle, we are going to prove laws of refraction and refraction. It means today's topic is using wave theory of light. It means Huygen's principle, prove laws of refraction and refraction. Okay, so let us start first topic. Proof of laws of refraction using Huygen's principle. You know that when we talk about Huygen's principle, it means wavefront, incident wavefront and reflected wavefront. So let us first suppose that this XY is a plane reflecting surface, and on this plane reflecting surface, AB is the incident wavefront. Wavefront AB is incident on this plane reflecting surface, and both this incident wavefront AB and reflecting surface XY are perpendicular to the plane of this board. It means if we are writing in a paper a copy, both these incident wavefront and reflecting surface is perpendicular to the plane of paper. And one more thing, you know that any line drawn perpendicular to this wavefront, that is called ray. So here this line QB and PA is perpendicular to this wavefront. It means this PA and QB are incident rays. Any ray perpendicular to the incident wavefront is called incident rays. Again, you draw one normal to this reflecting surface, and you know that the angle between this incident ray and this normal is angle of incidence I. Okay, and one more thing, this whole is what? This wavefront and this incident ray both are at 90 degree. So this angle is 90 degree. It means this angle becomes 90 minus I. Okay, and again this line is normal to the surface, so this whole angle is 90 degree, and this one is 90 minus I. It means this angle, this one is angle of incidence I, right? So you can write here first, this XY is a plane reflecting surface, right? And on this plane reflecting surface, wavefront is incident. So AB is plane incident wavefront. And this plane incident wavefront and reflecting surface, this XY, both are perpendicular to plane of, here I am writing plane of board, you write plane of paper, right? And the line perpendicular to this incident wavefront is called incident ray. Here PA and QB are incident rays. Okay, and this one is normal to this surface. So angle between this incident ray, you can write here, these are incident ray. Okay. And the angle between this incident ray and normal is angle of incidence. So you can write I is angle of incidence. Now suppose this wavefront, incident wavefront AB is moving with velocity v in this medium. V is velocity of wavefront, right? Now, according to Huygen's principle, this incident wavefront strikes this reflecting surface. First, the part A strikes the reflecting surface. At that time, B point is here. So, according to Huygen's principle, each point on this wavefront acts as a source of secondary disturbance. So after time t, suppose the disturbance from this B point reaches to point C here. By travelling distance, how much? V is the velocity, t is time. So total distance travelled by this B point to reach C is Vt. It means Vt, you can write also BC is equal to Vt. And at that time, the disturbance from this point A also reaches to this point D, because you know that now if it is a point source, then the wavefront, this is spherical in shape, right? And that secondary disturbance, this is called wavelet. So point B reaches to point C by travelling a distance, this BC is Vt. Then at that time A reaches to point D by travelling a distance Vt. Here this AD is also Vt, right? Now if you draw according to Huygen's principle, this is secondary wavelet, and if you draw a tangent on this secondary wavelet, you get next wavefront. This CD is called reflected wavefront, right? And if you draw one normal on this reflected wavefront, you get a ray, and here it is called reflected ray. So here CD is reflected wavefront, right? And this DS and CR are called reflected rays. And if you draw one normal here at this point to this surface, this one is normal, this one is reflected ray. So angle between this normal and reflected ray is angle of reflection. And you know this wavefront reflected and reflected rays are 90 degree to each, perpendicular to each other, right? This one is 90 degree. So this angle becomes what? 90 minus R, okay? This angle 90 minus R. And you know that this is normal to the surface, this whole is 90, right? And in this one is 90 minus R. So these angles, reflected wavefront and surface, is R. And R is called angle of reflection. So with the help of geometry, you can prove that the angle between this incident wavefront and reflecting surface is I, and this reflected wavefront and reflecting surface is R. Now I am going to prove laws of reflection. There are two laws of reflection. To prove this law, first I consider this triangle A, B and C, then ADC. So triangle ABC and DCB, I am going to prove these two triangles are congruent, so that angle I equal to angle R we can easily prove. So in triangle ABC and this DCA, in this one AC is common, right? In both triangles AC is common, and this angle ABC wavefront and 90 degree, and also this angle reflected and wavefront is 90 degree. So angle B equal to angle D, each is 90 degree, right? This each angle is 90 degree and this BC is common. And again one more thing, in this triangle DCA, AD is VT and here BC is also VT. Both distance is equal to VT. So in this way we can prove that triangle this ABC and DCA are congruent triangles, right? And if the triangle is congruent, so this angle in this triangle, this angle I is equal to in this triangle angle R. So in this way we can prove that angle of incidence is always equal to angle of reflection. This is first law. Angle of incidence is always equal to angle of reflection. Now one more law, you know that incident ray, reflected ray and normal all lie in the same plane. How you prove? You can prove easily with the help of this only theoretically, right? Here This one is incident wavefront AB, CD is reflected wavefront, and XY is what? Refracting surface. All these three are perpendicular to this plane of board, or in your copy, plane of paper. And this incident ray, this refracted ray, both are perpendicular to the incident wavefront, reflected wavefront, and also normal is perpendicular to this refracting surface. If incident wavefront, reflected wavefront and refracting surface are perpendicular to the plane of paper, then incident ray, reflected ray and normal are in the plane of paper. So you can easily prove second law also with the help of this geometry, right? Okay, first you take a screenshot, then I will write second law of reflection, right? Okay, shall I rub this one? Right, here this AB, incident wavefront, CD, reflected wavefront, and XY, reflecting surface, all are perpendicular to plane of, here I am writing board, you write plane of paper, right? And you know that if AB is incident ray, then this PA perpendicular to this incident wavefront is incident ray. So this PA is perpendicular to this AB, incident wavefront. Again CR, refracted ray, is perpendicular to the reflected wavefront CD, and also this normal is perpendicular to this reflecting surface. Normal is perpendicular to the reflecting surface XY. If all these three are perpendicular to the plane of board, it means this all three, incident ray, refracted ray and normal, are in the plane of paper. So you can easily write incident ray PA, you can write PA and QB also, then refracted ray CR and normal all lie in the plane of paper. You write paper, I am writing in the plane of board. So just theoretically you prove second law also. In this way, first you prove first law of reflection, angle of incidence equal to angle of reflection, and then incident ray, refracted ray and normal all lie in the same plane of paper, same plane of board. Okay, take a screenshot. Then next I am going to prove laws of refraction using Huygen's principle. Now I am going to prove laws of refraction using Huygen's principle. For this, let's suppose that this XY is a refracting surface which separates the two medium. This first one, upper one, is suppose rare and this lower one is tensor medium, and XY is a refracting surface which separates the two medium. Okay. And on this refracting surface, wavefront is incident on this one. So this AB is incident wavefront. AB is incident wavefront. Okay. And if you draw a normal to this incident wavefront, you get incident rays. So here PA and QB are incident rays, right? And this one is normal to the surface. The angle between this normal and incident ray is angle of incidence. So I is angle of incidence, right? One more thing, if this is angle I, this whole is 90 degree, right? Both this wavefront and rays are perpendicular to each other. So this becomes this angle 90 minus I. And again this is perpendicular to the surface, normal is perpendicular to the surface. This whole is 90 degree and this one is 90 minus I. It means this angle is I, angle of incidence, right? Now also suppose that this incident wavefront is moving with velocity v1 in the rare medium. v1 is velocity of incident wavefront, okay? Incident wavefront. And here also this incident wavefront and this refracting surface, these both are perpendicular to the plane of paper. You write here, I am writing to the plane of board, okay? Again I am going to use Huygen's principle to draw refracting wavefront. How you draw refracting wavefront? You know that according to Huygen's principle, each point acts as a source of secondary disturbance. So when this first A point of this wavefront strikes the refracting surface, and after striking it produces disturbance in all possible directions. Suppose at any time t, and when let's also suppose that v2 be the velocity of wavefront, refracted wavefront you write here, okay? And refraction takes place in denser medium, so v1 is greater than v2. Now after time t, suppose the disturbance from this B point reaches at this C point, okay? So you draw one secondary wavelet here, right? And this BC distance is how much? If it is moving with velocity v1, then v1t after time t, cover distance v1t. At the same time, this point A also reaches disturbance point to this point D. You again draw one secondary wavelet here, right? And this AD in this median velocity is v2. So this AD is v2t after time t. You cover distance. This AD is smaller than BC because v1 is greater than v2. So BC is greater than AD. Now if you draw a tangent to these secondary wavelets, you get a new wavefront. This wavefront is called refracted wavefront. Okay, so this CD is refracted wavefront. And if you draw a normal to this wavefront, you draw one normal. This one, this AD is refracted ray. Any line drawn normal to the wavefront is ray. So on refracted wavefront, you get refracted ray. And again, if you draw a normal, so this angle between this normal and refracted ray is called angle of refraction. And this whole angle is 90 degrees. So this becomes how much? 90 minus R. And this wavefront and ray is also perpendicular to each other. So this angle, this one is 90 minus R, this one is 90. So this becomes angle R. And this R is angle of refraction. So in this way, you draw the figure here. This incident wavefront and this refracting surface makes angle I. With the help of geometry, we can easily prove this one. And also this refracted wavefront and this refracting surface makes angle R. Okay. Now, I want to prove laws of refraction using this diagram. It means you know what is first law of refraction, that is Snell's law. Sine of angle of incidence to sine of angle of refraction is always some constant quantity. So you have to prove this one. For this, let us consider this triangle first, ABC. In triangle ABC, this one is 90 degree, right? This wavefront and ray is normal. This one is I. So you can easily find sine I. Sine I is what? Perpendicular by hypotenuse. So perpendicular here is what? this BC, and hypotenuse is AC. So sin I is BC by AC, and BC is how much? V1T by AC. Again, you take this triangle ADC. Here this angle is 90 degree. So this one is hypotenuse and this one is perpendicular. So sin R becomes AD by AC, and AD is what? AD here is V2T. AD is V2T and by AC. Now you divide these two equations, sin I and sin R. Then you get sin I by sin R equal to V1T. This AC cancel in the denominator, V1T by V2T. Again TT cancel, you get V1 by V2. And you know that velocity of light in any medium is constant. So the ratio of these two velocities is also a constant quantity. It means sin I by sin R is some constant. And this is what? Snell's law. If ray travels from first medium to another medium, you can write this constant equal to n2 from first n to 1. Okay, so you easily prove this first law of refraction. Again, with the help of geometry, theoretically you can prove second laws of refraction also. You know this refracting surface, this incident ray, and this AB is what? Sorry, here I am writing AB is incident wavefront. Okay, here I am writing wrong. Incident wavefront. Okay. To correct this sentence, AB is the incident wavefront, and this XY I have not written. Right, XY is refracting surface. Right here, refracting surface. So this refracting surface and this incident wavefront both are perpendicular to the plane of paper, and also this refracted wavefront, all three are mutually perpendicular to the plane of this board. And you know that this incident ray PA is what? This PA is perpendicular to the incident wavefront AB, right? And this refracted ray AD is perpendicular to this refracted ray DC. AD is perpendicular to DC, and also this normal is perpendicular to the refracting surface XY. Normal is perpendicular to the refracting surface XY. So if all these three, incident wavefront, refracted wavefront and this refracting surface, are perpendicular to the plane of this board, you write paper, it means all these three, incident ray, refracted ray and normal, are in the plane of board or plane of paper. So easily you can write incident ray PA here, refracted ray and normal all lie in the same plane of paper, right? So in this way you can prove laws of refraction using Huygen's principle. First law is this one, sin R by sin R is some constant quantity, Snell's law, and second one is this one. Incident ray, refracted ray and normal all lie in the same plane of paper. Okay, hope you understood these topics. Please take a screenshot of this one. So after this I am going to end the class. In the next class, we will start new topic, interference of waves. In that one, we will also discuss principle of superposition of waves. What are the conditions for maxima, minima, constructive, destructive interference, everything we will discuss in the next class. Hope you understood all these topics. Okay, up to the rest students, bye-bye. Wait for the next video.